Hey everybody, it's Mr. Slomka. We are going to be talking about section 12.3 today. This is a very important section because we're going to be discussing derivatives, which is something I've talked about a couple times in class, and it's one of the major things that you're going to learn in the first couple chapters of calculus. So it'll help you out this year and it'll help you out next year. So today is really the first big day. It doesn't say derivative up here at the top, but it says something else that's very similar. It says tangent line, which we'll be talking about as well. So this is a basic concept that once again is going to be getting us closer to a derivative. So right up here it says lots of today's lesson will be focusing on rates of change. There is a lot of emphasis on rates of change in calculus, so we will begin to visit them now. Rates of change are directly related to a derivative. You can use a derivative to find a rate of change. Now you have probably heard the term rate of change before, but you don't use it very often. The term that is used more often is the term slope. So when you hear the term rate of change, what you really mean is slope, or that's what we mean. We will be finding slopes today, but rather than finding them of just nice, easy straight lines, which you are probably very good at finding the slope of, we will be finding the slopes of some curves, and that'll be a little bit tougher, like parabolas. So, when I say how can you find the slope of a curve? Well, you really can't. But what you can do is you can find the slope of a tangent line, a line that is tangent to the curve. Now, if you're thinking tangent in like the sine, cosine, tangent way, this is a little bit different. It's related, but not quite the same thing. A tangent line is a line that intersects a curve at exactly one point, and it represents the slope of the graph at that one point. So here's a couple pictures right here. This one's a nice parabola, and if I wanted to draw the tangent line through this point right here, what I'd have to do is I'd have to draw a straight line that mimicked the basic shape of that curve, but it has to be straight and it only touches at one spot. So a lot of times what people think is, oh, I will just make a nice horizontal line. Well, that doesn't really follow the trend. The trend right here is going down, and it's going down pretty steeply over here and a little bit more mellow over here. So what's going to happen is that this red line that I just created is actually a bad one. Let's draw a better one in black. So what I'm noticing is once again pretty steep, and it needs to touch that point just once. And so I'm going to draw a tangent line that looks a lot more like this. You see how it kind of lines up right next to it? It just brushes against the graph and then it rolls on from there. If I had extended this red line, it actually crossed the graph a second time, so that would be bad as well. If I extend this black line, it will never cross the graph again. It's just at this one point, and that's it. So that's a very good tangent line. Now down here at the bottom, this one can cause a lot of issues for some people. Once again, a lot of times what people want to do is they want to draw a nice straight line, and especially for this one actually works out really well. If you draw a vertical line right up and down, it will only cross the graph one time, and that seems like a really good idea. That's actually a symmetry line. We don't want that. We want a tangent line. So what's happening here is that we are once again coming down, and then we're coming through, and then we're going to head back up. So if you'd like, what you can do is you can kind of use your pen and kind of roll it around through that point right there. That's pretty much the line that we want to make, and then we're going to roll right back up through the curve right there. So right about here, that's what what we're really after. There's a fancy name for this point. There's a couple fancy names. One of them is that is the vertex. And the other one is that it's also called a turning point. And it's a turning point because what you have is you have kind of like this decrease in your tangent line slope, and then right here it changes and it becomes an increase in your tangent line slope. So it's going to have a nice flat horizontal line. So that one's going to be the good one. Touches the graph exactly one spot, and it follows the general kind of trend of the graph. So that one's going to be a good one. Same thing over here. What if I want to do a tangent line for this guy? Well, once again, I kind of have to follow that general trend. It looks like it's going up, so I don't want to change it and go in the opposite direction. I want to follow that same trend, so I'm going to be drawing a tangent line that kind of looks like this. Now, a lot of people, what they'll do is they'll say, hey, Mr. Slomka, if you extend this one, it's going to cross. Isn't that bad? Well, here's the thing. When you're drawing these tangent lines and it says that it can only cross exactly once, what it really means is in a relatively close area. So if I decrease the domain to just this area that's right around the point, then no, it does not cross. If you extend a little bit further, this graph makes a pretty intense corner right here, and then all of a sudden it's capable of crossing. So that's kind of outside the bounds of what we're interested in. It can't cross when you get close to the point. So somewhere around here is where it can't cross. So make sure you're following the trend and make sure that you're sticking to that idea of only crossing the graph once. But if you're going to flub a little bit, that's okay. But don't do anything dramatic like this line here. So you want to just avoid that. Now we just drew some lines, and I could kind of tell you about the slope. Like I know this one's going to be negative and steep, and that one's horizontal, so it's got a slope of 0, and that one's pretty shallow and positive, but if you want to be more specific, somebody's going to have to draw the tangent line for you. Your calculator could draw tangent lines for you, and computer programs can, and I will oftentimes just draw a tangent line for you, and you'll just need to tell me about them. So it says right here, approximate the slope of the curve at the points. So I've got a point right here, and it's got a tangent line, and I want to know what the slope is. Now this one, it's only got one point. It's got that point right there, and then there's a nice line. This is once again another turning point. It's not a vertex anymore, but it is a turning point. And because it's a turning point, it's got that horizontal line. All horizontal lines have the exact same slope. That slope is 0. Vertical lines are undefined. Horizontal lines have the slope of 0. So that one works out okay. Now B is a little bit more intense and a little bit more par for the course. What we have right here is we've got a tangent line, and it's going along this really sharp or steep portion of our curve right there. So it's a pretty close to vertical line. It's got one point that's right here, and then they did something very generous, and they told you about one extra point. It's not on the curve, it just is on the tangent line, that's all. So what you're going to do is you're going to end up having to use both of these points right here to calculate slope in a typical way that we've done many times before. y2 minus y1, x2 minus x1. So that's going to be 2.5 minus 0. There's your y values right there, and then your x values can be 1 minus the 0.66. There you go. So in our numerator, we're going to subtract, which is going to give us 2.5, and the denominator we're going to subtract, which is going to give us about 0.34. I'm rounding. I see decimals, so if we write our answer as a decimal, that kind of makes a lot of sense. Once again, it's a pretty steep line, so I'm looking for a big slope. That's a good thing to try and get into the habit of, knowing what you're going to expect. So when you divide these two, you get a value 7.35. Once again, I've rounded. And that value is big. That's a rise of 7.35 over a run of 1. So definitely a lot more rise than it is run, which makes sense when you look at that line that is very, very close to vertical. So right there, there's your good answer. You don't have to write the denominator of 1 if you don't want to. You can just write it as 7.35. Okay, so now none of this really has to do with limits. So how are we going to bring limits in here? Well, here's what's going to happen. We're actually going to start off, we're going to use limits, and we're going to start off with something called a secant line. Now, a secant line is very closely related to a tangent line, but it actually touches your graph at 2 spots. So what we have is we've got a spot right here, and then we've got another spot right here. And you know how with limits, how what you're doing is you're approaching a certain value? You're going to do the same thing here. What you're going to do is you are going to shrink the distance between the 2 points that form your secant line. And as you do that, what's going to happen is that this dot is going to move up, 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 closer, 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 until eventually the 2 dots sit on top of each other, and your secant line becomes a tangent line. That is going to be how the limit comes into here. So it's hard to actually create a tangent line, so what we're going to do is we're going to approach this tangent line, and we're going to create it slowly but surely, so by moving our dot closer and closer and closer together. So that's what we're really doing. So the secant line is cool, and I'm glad that we're talking about it, but the main thing is shooting for that tangent line. So that's what we're really after. Tangent line is the big term for today. Here's the big formula for today. In order to do this, what we have right here is we've got our function right here, or our equation right here, for a slope of our tangent line. F of x plus h represents this point right here that is moving closer and closer and closer, and then f of x represents the point that we're trying to get close to. So we've got our 2 points, and they're getting closer and closer and closer. That's why it's subtraction, because they're getting closer to the point where they're right on top of each other. H represents the distance between those two things, and as you can tell right here, h is going to 0. So once again, they're getting closer, 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 because h is going to 0. So you can see it all kind of makes sense right there. It all works well together. This right here is a thing that we actually worked on yesterday, and I had even alluded to the fact that it's related to derivatives, and now you can kind of see a little bit more. So the derivative has to do with this rates of change. The rates of change have to do with tangent lines, and the way that we get to our slope of our tangent line is by using this guy right here. Okay, so that's a lot of information. Works out really well. Let's try some. So back here, what we've got is we've got a couple of example problems, and they're set up very much the same, but there's only a couple slight changes between them, so I want to make sure that I hit on those, so I've got a couple to do that. So our first one's a very nice one. It's also a very easy one. If you take a look right here, it says f of x is equal to x squared. That's it. We did a tougher one yesterday, and it says that we want to find the slope of f of x is equal to x squared at the point -3, 9. So if you wanted to make a quick sketch of this, that wouldn't be a terrible idea. X squared is just a regular parabola. It's going to kind of look like this. And you don't have to draw this all the time, but you might want to just visualize it, or you could use your calculator to do it. Then the point that we're interested in is -3 units over, which is a short distance over, and kind of far up. So it's going to be a point like right here. We're trying to find the tangent line slope. It's going to look a bit like this. It's probably going to be pretty steep and pretty negative. So that's what we're kind of shooting for. Here's how we're going to create it. So what I have is I've got our pattern right here that'll help us find the slope of a tangent line. And what we're going to use is we're going to use this f of x, and specifically right here and right here where it says x, we're going to use the x value that was given to us, -3. So a lot of people say, what about the y value? What about the 9? Well, I'll be honest with you. The 9 really doesn't help us out too much. The x value is the one that we want. That's what you use to get your 2 points close together. You eliminate y values, or you eliminate the y value, you only use the x value. So if you take a look right here, it no longer says f of x plus h, it says -3 plus h, and it says f of -3 instead of f of x, because of that -3 right there. Okay, so now let's put it to work. So we're still working on a limit, and it's going to be as h approaches 0. Now my f function right here, my f function is basically x squared, or more specifically, whatever is in the parentheses gets squared. And the same thing over here. I'm going to have another f function, which is once again another whatever's in the parentheses gets squared situation. So that's basically the limit that I'm after. Now I'm going to use two different things in here. For my first f function, it says that I need to use a -3 plus h. So in this first set of parentheses, I'm also going to put -3 plus h. In the second f function, it says that I need to use just -3. So in the second parentheses with s squared, I'm going to use just -3. This right here is a limit that we're going to work on. There's a lot of opportunities to simplify. I have foiling, I have order of operations, I got lots of stuff, so let's make it look pretty. When I'm doing this work, when I'm simplifying, I need to make sure that I write the limit as h approaches 0 in front every single time. You need to write that out in front every single time. So I'm going to FOIL this out right here. That is going to be like -3 times -3, which is going to be 9. And then you have -3h and another -3h, which is going to give you -6h. And then h times h is going to be h squared. Over here, this one's a tricky one. You have a -3 that's being squared, so it's going to be a +9, but you also have a minus sign right here, so it actually becomes minus a +9 or just -9. And our denominator is still h. So now something really great happens here. Same thing that happened last time, yesterday. Our constant terms are going to cancel out, just like what happened yesterday. This is really awesome. If you take a look at the only terms that are left, we only have h terms. I'm going to clean this up a little bit. I like to have my h squared term first and my h term second, so I'm going to do that. So this is going to be the limit as h approaches 0, and it's going to be h squared first. Then I'm going to have my -6h, and then I'll have my h on the bottom right there. Cool. Now yesterday what we talked about is if this is an h and this is an h and this is h, you can cancel out, and the same thing's going to happen right here. Formally what you should do is you should factor out the h from the two top terms, and then you can cancel out with the denominator. And that's what we did yesterday. And if you want to see an example of that, you can take a look at yesterday's video. The other thing that you can do, which is a little bit faster, and I'm okay with it, is if you just cancel out your h's right here. Now the one thing that I might mention is this guy is h squared, so you're actually going to retain one of your h's, but you're going to drop the other. So what I like to do is I like to cross out the power to remind myself that I'm going to keep this one, but I'm going to lose one of the other ones. So that's a little bit of a faster way, which is an okay shortcut in my opinion, so I'm going to let it slide. Not the most thorough, but pretty good. So what's left over? Well, we're going to have an h, like I'd mentioned. It's not going to drop all of them. And then we'll have a -6. That's not going away. But there's nothing in the denominator, so that's all you have. That's really, really nice. That is so nice that what we could do is we can use direct substitution. So that's exactly what we're going to do. We're going to direct substitute in there. We're going to end up with 0 minus 6. Now, if you take a look, this is the very first step that we've done where we haven't written limit. And that's because when you direct substitute, you're essentially taking the limit. And so I now have this thing that does not have a limit, and I'm going to simplify it, and I get the answer of -6. There you go. That right there is the slope of our tangent line that we had drawn earlier. If you take a look at that tangent line that we drew, it was very negative and it was very steep. And this guy is definitely both of those things. Specific, it's -6 over 1. That means you go 6 units down for every 1 unit you go over. I'll buy it. Definitely looks like that to me, so I'm satisfied with my answer. Here's another example that's similar but a little bit less information. This time it just says find the slope of the equation. But it doesn't actually tell you a point. So up here we had a point, which was very helpful, and we used that. We used it to get rid of some x's. This time, we don't have a point, but it's okay. What you're actually going to do is, instead of actually finding the slope, what you're going to do is you're going to find an equation that will tell you the slope of any tangent line on the curve. So this is a little bit more general and a little bit more helpful. So this is something that we're kind of working towards. Giving you the point right here is actually a bit of a crutch. So I want you to work more towards this goal right here where I don't give you a point. Now the thing that's going to make this tougher is that there's going to be two variables in there. So you have to watch out for that, but it's okay. We'll go slow and it'll work out fine. So let's see what's going to happen here. So I'm going to start off with limit, and it's going to be as h approaches 0. Now for my first one is f of x plus h. Well, here's f of x right here. You got your -3, and then this is where the variable lives, so I'm going to leave it as a parentheses and over +5 at the back there. Then I've got another f of x that I'm going to use, but this one's a subtraction, so I'm going to minus, and I'm going to put another f of x function, -3, and this is where the x lives, but we're going to leave it as a blank right now, and we're going to put a +5 at the back. And the whole thing's over h. There's your setup right there. So, once again, I'm going to use some of these things and put them into parentheses. So, I have x plus h here, which means I'm going to put an x, and I'm going to have an h in there. So, we're going to have both things. And over here, for this one, I'm going to have f of x. So, that one is actually going to be the exact same as what we had right up here. It doesn't change at all. Okay, so now we got two variables. That's okay. We can continue to work, and we're going to do the same things that we've done before. So simplify, make it look pretty, and then maybe direct substitute. So let's see what we can do. I'm going to try and simplify some of this stuff right here and some of this stuff right over here. So start with the distributive property. So I'm still writing limit as h approaches 0, and that is going to be -3 times x, which is going to be -3x. And -3 times h, which is going to be -3h. And I have my +5 right here, so hold on to that +5. Over here, not a lot I can do just yet. I'm just going to have my -3x. I can write that a little smaller and nicer, and then I can have my +5. Something I wanted to point out to you, and why I'm going slow here, is because I have a set of parentheses. You need to make sure you put the set of parentheses on here because it's going to really help you in this next step. If you forget your set of parentheses, what's going to end up happening a lot of times is that 3 becomes positive, but the 5 stays positive. And what we really need to have happen is the distributive property. So that means the 3 becomes positive and the 5 becomes negative. That is going to be extremely important in our next step. So let's take a look at what happens here, and then we'll talk about that next step. So work's going to come up here. Once again, still limit as h approaches 0. That's not going to change anytime soon. And now let's write down some stuff. So I've got a -3x. I've got a -3h. I got a +5. I'm now going to have a +3x. Are you seeing the good stuff? And we're going to have a -5. And the whole thing's over h. There you go. Okay, so here's the really, really cool part. -3x, +3x, gone. +5, -5, gone. Great, that worked out really, really nicely. So then what's going to happen here is we're only left with a couple of things. So you might have worried at the beginning, oh my gosh, there's so many variables, I don't know what to do. Well, it works out okay. Well, a bunch of the variables just dropped out, and all we have now is just -3h over h. And similar to the last example we were just working on, h is a common factor, so we can actually cancel out both of those guys. This is also a weird point for some people. It becomes so small and compact that they actually start to panic a little bit. They say, oh my goodness, my h is approaching 0, but all I have is a -3. I actually got rid of all my h's. What am I going to do? Well, here's the thing. You're taking the limit of a constant term, which is we actually have a rule for. And the rule is that if you're trying to take the limit of a constant term, you will get the constant term every single time. So there is no h to worry about, so you don't have to worry about the fact that you're going to 0. You're just going to get -3. So there's your answer right there. That worked out pretty well. Now let's take a pause for the cause before we move on to our next one right here. If you look closely at the question that is being asked of us, what we were really being asked about was slope. Take a look at that equation right there. What kind of graph is that equation going to give you? Well, it's just a line. It's actually a line in slope-intercept form. 5 right here is the y-intercept, and surprising, or maybe not so surprising, 3 is actually the slope, or more specifically -3. We had the slope the whole time. It was -3. We knew it was going to be -3, or at least you could have known that it was going to be -3. We went through this work right here using our derivative formula, and we found out that it was the exact same slope. The boring thing about this guy is that it's just a line, so the tangent line is the line itself. The slopes stay the same. So it's not as exciting or interesting as this one right up here. toss that one in there because it's a good, easy example. It's also too easy for any kind of test or assessment, so don't expect to see one this easy in the near future again. Let's do one that's only slightly harder. So now what we have is we've got this guy right here. Once again, we're going back to a parabola, and it's only got a little vertical translation on it, so it's nothing particularly crazy. This one also says find the slope, but it doesn't give you a point. So we're working towards that goal once again. My goal is to get bigger and uglier equations all the time, so we're just moving towards these big challenging equations. So these ones are very, very small and easy, but we're going to keep practicing, keep working on it until we get to some big, ugly ones. So let's try it out. So I'm going to try and do this one a little bit faster. So I'm going to set up my limit, and I'm just going to go all right as fast as I can with my setup. So for my first one, it's f of x plus h. That's x plus h is going to go right here where the x usually sits. So it's now going to be x plus h squared. And don't forget about your minus 2, because this time it has a minus 2 at the back. Then it says minus f of x. Now here's a really, really nice thing. What you have right here is f of x, and what you have over here is f of x. So what you can do is you can just copy down what you see behind your minus sign. So I'm going to copy it down, x squared minus 2. Now, if you look what I did right there, I've made a big mistake. When I was subtracting right here, minus f of x, I was supposed to subtract the whole chunk. But if you look at it right now, what it really looks like is minus x squared, and the negative 2 is just doing whatever it was doing before. What really needs to happen is that you need to subtract that whole chunk right there. So that means that's going to be dealt with a little bit differently than it would have been otherwise. So it's important to put those parentheses on there. Parentheses are important. Limit notation is important. There's lots of little tiny tedious important things. Dividing by h is also very important. So let's do it. I'm going to simplify. I'm going to FOIL this. This foiling is going to be a little dissatisfying for some people. X times x will give you x squared, and then you're going to have x times h and another x times h, which is actually going to be 2xh. Then what's going to happen is you have h squared. We still have a minus 2 at the back there, so we'll keep our minus 2. And then now, here's where our distributive property is going to come into play. We're going to distribute that guy, which is going to be negative x squared, very important, and we'll have a positive 2, also very important. The whole thing gets divided by h. There it is. All right, now this is why it's so important. You can make sure everything works the way it needs to. If it doesn't work the way it needs to, this next step's not going to work out really well. Here are some great things. This negative 2 and this positive 2 are going to cancel out. And if that 2 had stayed negative, that would have never happened. Also, this negative x squared and this positive x squared are going to cancel out. That's really important too. Take a look. The only terms you have left all have a common factor, which is really, really exciting, and it's going to make our problem flow really nicely. So let's take a look at what happens now. So our limit as h approaches 0, and our terms that we have are, I'm going to write my squared term first, h squared, then I'll have my 2xh, and the whole thing's over h. As I've mentioned many times, you have this common factor showing up, so if you want to cheat a little bit, you can start canceling some of these guys out. So now, once again, I've also done something here that I don't necessarily love. Right here, I have h squared, and I crossed out the h. This makes it confusing. It makes it seem like the whole term disappears, so I don't really like to do it like this. What I like to do is I actually like to cross out the power, and I keep the h how it was. So I'm going to rewrite this guy. Make sure I hold on to one of those h's. Don't lose them all. So we'll have our h, and right over here, we lost the h, but we were retaining the 2 and the x. So we'll have h plus 2x right there. All right, now for your last piece right here, you're still taking the limit, and when you're doing this limit, I need you to really, really make sure you're following the rules. This says that as h approaches 0. That rule does not affect x in any way. They're not related to each other. So that means we're going to leave x out of our next kind of calculation. It'll be there, but we're just not going to do anything with it. So for our direct substitution, we're only direct substituting to the h. That's the thing that turns into a 0. I don't need to write limit anymore. I'm just going to write it with a 0 in there. Then, when we simplify, it's okay that an x is part of our equation. What we get is we just get 2x. More specifically, this whole thing that we were working on, if you take a look right over here, it was equal to m. That really means that m is equal to 2x. This is a formula that will tell you about a slope of a tangent line. Any x value you plug in right here will give you the slope of the tangent line. So then for our last piece right down here, it says use your new formula to find the slope at the point -3,7 and 1, -1. So I'm going to try and find these two tangent line slopes. If you wanted to make a quick drawing, you could do that. Our equation right here, f of x is equal to x squared minus 2. That is once again just a pretty typical normal parabola. And if we're interested in points like -3,7, that's going to be a point like right up here. It's going to have a very, very, very steep negative tangent line that kind of looks like this. And this one right here, negative, or 1, negative 1, which is going to be like right around here. This one's going to have a positive slope, and it's going to be a little bit more subtle. So it'll be close, not as steep as the other one. So let's see if we can find those two slopes right there. So to do these, the main thing that you need to also remember is that to find the slope, you only need the x value. So once again, kind of like at the top of the page, I really don't need the y values at all. They're not particularly important for me. So I'm going to use this formula with the negative 3, and I'm going to use this formula with the positive 1. That's going to be 2 times negative 3, and it's also going to be 2 times 1. So for my first slope, the one that was supposed to be steep and negative, I get negative 6. Great, that is definitely steep and definitely negative. And for this one, the one that was supposed to be positive and a little bit more subtle, I get m is equal to 2. Once again, positive and a little bit more subtle. So that works out really, really nicely. There you go. We are working our way towards taking derivatives. These are your first couple derivatives, and they focus very, very heavily on rate of change, slope. We'll do some more of these derivative things tomorrow. If you are working on your AP test, good luck. I'll see you soon.